Uh, in last class about the waves and sound chapter, we discussed wave, different types of waves, characteristics of waves, and transverse waves, longitudinal waves, and standing waves, and the phenomenon of beats we discussed in last chapter. In today, we are going to discuss about Doppler effect, echoes, reverberation, Sabine's formula, conditions for good auditorium, and resonance. In this chapter, we cover these topics. A Doppler effect. What is a Doppler effect? You are all aware when you are going to your homes or you are coming from your home to college, you travel through by bus or by train. If you are coming from your home to college by the railway, you reaches the railway station and you are waiting for train on a platform. When the train is coming to the platform, you moves here and there, whether you have to go to left or you have to go to right, front or back for seats. If your seat is reserved, no problem. But if you are planning to come by general, then you go to the back side of the platform or the front side of the platform because due to the traffic and to get the seat, right? If you are going backside of the train and the train is coming to the platform, then the rail engine makes blows horns and you listens the horn sound. When it approaches you, you listen more sound, more intense sound. It is passing away from you. You are going back. Returning passing you. Then you listen less sound. Here, actually, the sound source is a horn of a rail engine. Will it decreases or increases the sound when you are going back? No, it is not changing its frequency. Just you are moving and the train is also moving. That's why you are listening different frequencies, whether it's a decreased or increased one. If it is coming to you, approaches you, you heard more sound. If it is going away from you, you heard less sound. This effect, the increase in the decrease, increase and the decrease, this is called as a apparent change. Actual change is not there, but the listening change is there. The apparent change in the frequency of a sound you are hearing due to the relative motion between the observer and the source is called as a Doppler effect. See here, the vehicle is approaching one person. He hears high frequency. Who is away from the vehicle listens less frequency sound. So really, the vehicle is this horn is blowing less and more. No, it is blowing at the same frequency, but the observer's frequency, those who are getting the frequency with the increased intensity or decreased intensity, the apparent change in the frequency of a source of sound due to the relative motion between the observer and source of the sound is called as a Doppler effect. What is the relative motion? Relative motion means with respect to one, another one is a moving. Sometimes in Doppler effect, we have different conditions in Doppler effect. For example, different cases here, when the source is moving and observer is at rest, source is moving, observer is at rest, and in another case observer is moving, source is at rest. So when source is at rest, observer is moving away from the source and coming towards the source. When the observer is at rest, source is coming towards the observer and going away from the observer. And in some conditions, both observer and source both are in motion, they are coming together, and another case is they are going away from the motion, away from it. So when the observer is at rest and source is coming towards the observer, then apparent frequency increases. So observer listens more frequency or more sound. If the observer is at rest position but the source is going away from the observer, then he listens lesser decreased frequency. If the observer is moving, the source is at rest, whatever, if which is a rest or which is moving, whatever it may be, if they are approaching, the intensity in frequency increases, they are going away from the frequency decreases. The observer is moving away from the rest source, then its frequency, when it is the observer or source going away, frequency decreases, they are coming approaching together, frequency increases. This is a Doppler effect. We have a different applications of Doppler effect. So Doppler effect is used to navigate. Doppler effect is used to navigate aircrafts, and it is used to measure the speed and direction of flow of vessels. It is used in a measure the speed of automobiles, to accurate bombing, to calculate the velocity of sound, determine the velocity of stars relative to the earth, to understand the theory of expansion of universe, determine the velocities of planets and stars, to track the earth satellites. The velocity of sound can be calculated using Doppler effect, and it is also used in medical and engineering sectors. By the Doppler effect, the double stars are detected using Doppler effect. Saturn rings are detected by using Doppler effect. This effect is used in determination of velocities of stars relative to the earth, the rotation of Saturn rings and double stars detected using Doppler effect. In medicine, the Doppler effect used to study the heartbeats, blood flow, speed and direction of blood flow in different parts of the body. They uses ultrasonic waves, and it is commonly called as a sonography. In sonography, they are using Doppler effect. To study the heart functioning, determine the speed and direction of blood flow in the heart, echocardiogram, we are using Doppler effect. And Doppler radar is a specialized radars used to use the Doppler effect to produce velocity data about the objects at a distance, to navigate and find out the velocities of different relative stars are the relative bodies, celestial bodies in a universe. And the Doppler effect is used in finding out the abnormal growth of a brain. Certain tumors can be detected by the ultrasonic waves using the Doppler effect. Doppler effect using the Doppler effect, the function of heart can be is seen in the form of picture generated echocardiogram. Ultrasonic scanning is based on this Doppler effect. It is used to locate the stones from the kidney, and the size of stones can be estimated. In engineering, the Doppler effect used in a radar system. In radar system, the velocity and directions of a motion of a targeted objects can be calculated. This principle is used in aerospace navigation to calculate the flying objects like drone, jet planes. It is utilized in a military sector, and used at airports to guide the aircrafts, used to detect the enemy aircrafts. Doppler effect also used to detect flaws in the metals. These are the some of the applications of Doppler effect we are using extensively in the field of medicine and the field of engineering and other sectors. If now another concept is, if a sound wave is produced and it is propagating through the medium in air, when it touches any obstacle, then it comes back, it bounces back into the same medium, and it is heard by the observer. It is heard by the observer. This shows the property of the reflection of sound. The sound waves can reflect, refract, interfere, diffract, but cannot be polarized. So sound waves shows the reflection. Here the reflected back sound is called as a echo. When it produced and it reaches some obstacle at certain distance, it comes back, right? He hears a reflected sound. The reflected sound is called as an echo. The reflected sound from a distance obstacle is called as an echo. For example, sounds from the nearby reflecting surfaces and buildings, sounds from the surface of a water in a well, sounds from the surface of a mountain or a cliff. If you go to the near to the well and produce sound loudly, shouting loudly, then you heard some sound inside the well which is produced by the you. It is same. So the on the surface of the water, the sound reflects back, bounces back, and you are hearing your own voice. That is called a echo. Here, echo, to listen an echo, you need some distance. For example, this is an obstacle. You are producing sound from here. This is the original sound, and you are listening the same sound after some time t. This is some distance it traveled. This is the distance traveled. Right? It has taken some time, that is t. If the time t, then velocity equals to displacement by time. Here you are listening the reflected sound. This is the original sound, and this one is a reflected sound. So d distance it original and d covered by displacement by time. So that is 2d by t, 2d by t, that equals to v. The velocity can be 2d by t. Here velocity equals to velocity equals to two d by now velocity equals to distance by t. So one distance is going original, one is a reflected. So this is the d distance, right? So d plus d, 2d. So there from this the distance traveled equals to v into t by 2. This is the distance vt by 2. So what is the distance here? What is the actual distance? If the velocity of sound, so d can be d equals to v t by 2. So v at 0 degree Celsius sound velocity is 330 meter per second and persistence time is 0.1 second. So d can be calculated, d equals to 330 into 0.1 by 2, that equals to 16.5 meters. 16.5 meters. This is the minimum distance to listen an echo. D is the minimum distance. If you take the 331 or 331, then you will get a 17 meters. That is the minimum required distance to listen an echo. If the source and the obstacle is less than the 16.5 meters, then you are not able to listen an echo, right? So here we have different applications in daily life using echoes. The echo application, majorly these echoes are used in a sonar system. Sonar means sound navigation and ranging. By using sonar you are navigating something. So this is a transmitter in a shape. It has a transmitter, it produces some echoes, it produces some sound. Due to the sound is coming down and at the obstacle it reflects back. So by using this sonar system we are able to find the depth of the seas, depth of the oceans, and the submarines underwater. The valuable things are submerged ships in the water, and height and direction of velocity of flying objects can be determined by using ecosystem. The velocity of sound can be estimated by using sound. We can estimate the velocity. The position and distance of an object, moving object, can be determined. Echoes are used in a medical field. In medical field, ultrasonic scanning we are using. This ultrasonic scanning is used to find the tumors in the body and stones in the kidney, and to study the uh, growth and condition of a fetus and womb. By using We are studying all these by using ultrasonic scanning. It based on the echoes, reflection of echoes, and the stethoscope also works on the multiple reflections of a sound. You can observing all the characteristics of the echoes, position and direction of moving object can be determined, right? So ultrasonic scanning is used extensively in the field of medicine to study and to find the tumors and kidney stones and any other defects or any other uh, parts defects inside the body, and the growth of the fetus, the growth of the and the condition of the womb. These are all the benefits and applications of the um, echoes, right? These are the applications of echoes we are using in the field. We are using extensively in the sonar system and calculating the sea depth and height objects and the moving celestial bodies and enemy aircrafts, enemy drones. Using echoes we can find out all these and their velocities and directions, and we are extensively using this uh, ultrasonic sonic scanning in a field of medical, right? Next, if this sound reflects back once, it is called an echo. When you enter into a new hall or a new building and produce some sound, a simple sound like oh, any sound you produce, then you heard some rough reflected sound multiple times. You heard some reflected sound multiple times with a lesser intensity or decreased intensity. This phenomena is called as a reverberation. For example, see this here, the sound source is here, the observer is here. When sound is produced from the source, the person listens direct sound, and the produced sound moves in all the directions, and he listens some multiple reflected sounds, sometimes reflected from the single wall and sometimes double, like that he is listening. When the observer is listening repeated sound, the sum of the sound, when the sound incidents on the walls, then it is observed by wall. Some part of the sound is observed by the wall, so he listens lesser intense sound repeatedly. This phenomena is called as a reverberation. The persistence of a sound in enclosed persistence of sound in an enclosure as a result of continuous reflection of sound at the walls even after the sound source has been switched off. If you are stopping the sound source, switching off the sound source, then even though you are listening the sound with decreased intensity, this is called as reverberation. Here you need some minimum intensity to listen this reverberating multiple reflected sound. So when at which minimum intensity the sound disappears, you are unable to hear the sound. That intensity is called as a threshold of audibility. The sound is reflected some number of times, and at certain frequency it is inaudible. You are unable to listen the sound. That minimum frequency or the minimum intensity of the reflected sound is called as a threshold of audibility. And after, when the sound source is switched off, the sound produced is remains in the enclosure or remains in the hall for certain time, and then it disappears, or its intensity decreases due to the absorbing material inside the hall or by the walls absorption. So the time required by the sound intensity, some time required to sound intensity to decrease the threshold of audibility from an initial intensity. 10 times of this sound is 10 power 6 times of this sound after the sound source is switched off. This is called as the reverberation time. The time required to sound intensity, required by the sound intensity to decrease the threshold of audibility from its initial position to 10 power 6 times after the sound source is switched off. It is called as a reverberation time, or it can be defined as the time taken to reduce the original sound intensity level by a factor of 1 millionth 10 power 6 after the sound is turned off. 10 power 6 times after the sound switched off, it is called as a reverberation time. So you can explain, for example, this is a source, S, a person is observer O, the sound is coming from the source, is directly coming, and it is 2 times reflected, right? For example, A, B, C, and another one is a direct only one time reflected at one surface, another one is 2 times or 3 times reflected, right? You can explain by this way. If the question rises, explain the reverberation, right? So the reverberation time is a time required by the sound intensity to decrease the threshold of audibility from the initial intensity of 10 power 6 times of this after the sound source is switched off. The reverberation time depends on the size of the room or the auditorium or the hall and the nature of the reflecting materials on the wall, the ceiling area, reflecting surfaces. The reverberation should not be very large or very small. Reverberation time depends on the size of a auditorium or the size of a hall and the nature of reflecting materials on the ceiling, on the walls, on the floor. This reverberation time should not be very small or very large. If the reverberation time is very large, the clarity of sound is lost. Before pronouncing the second syllable, the intensity of first syllable falls below the threshold audibility. Otherwise, listener receives the combined effect. If the reverberation time is too small, then by sound produced by less energetic sources is not audible at some places in the room. The reverberation time is selected keeping these 2 points in the view of the purpose of which is enclosed is design. Optimum reverberation time lies between the 0.5 to 1 second. The optimum reverberation time is 0.5 to 1 second. Reverberation depends on this volume of the hall, absorption power of the hall, intensity of sound produced, frequency of the sound. These are the factors affect the reverberation. So this reverberation time is important in the buildings, construction building. So the W.C. Sabine given a formula for this. He is known as the father of building acoustics. So, according to the Sabine, according to the Sabine, reverberation time is a most important factor in architectural acoustics or building acoustics. After conducting many experiments, he deduced a formula. He deduced a formula is called as Sabine's formula. Experimentally, he proved the reverberation time is proportional to the volume of the hall. Reverberation time T is proportional to the volume of the hall. T is directly proportional to V, where the T is the reverberation time. T is the reverberation time, V is the volume of a hall or a volume of a auditorium, volume of a building. And the enclosure, volume of a enclosure containing absorption is absorbing material. It has absorbing material. The absorption is inversely proportional to this reverberation time. According to the Sabine, reverberation time is directly proportional to the volume of the hall and inversely proportional to the absorption. So T is directly proportional to V by A. So T equals to some constant K into V by A. This is known as a Sabine formula, where K is a constant. The reverberation time is independent. Reverberation time is independent of shape of the hall, position of the sound, source of sound and listener, where they are sitting. Reverberation time is independent of the shape, whether it is constructed like this or any other shape, the building, or it is square or the rectangular or it's an oval shaped, whatever it may be, and the position of source and the position of the source and the position of the listener. It is independent, right? So KV by A, it is independent. Here, if A is the absorption coefficient of the substance and S is the surface area, then total absorption A can be written as summation of AI SI. I can take from 0 to N. It can take from 1 to N. 1 to N. A is the absorption coefficient of a material and S is the surface area. In a hall, we have different absorption areas. For example, open window is the best absorbing material of a sound, and doors, mat, furniture, all comes under the absorbing material, right? So absorbing material coefficient is, for example, the open window coefficient is 1 and the area is some 1 meter square, right? Then that gives the total absorption of that particular area, and you have to add the number of how many surfaces are there, how many different absorbing materials are available. Then it is given by the summation of AI SI. Here the experimentally the value of reverberation time T can be given T equals to 0.165 V by A. Sometimes this can be given as 1.17 V by A. 65 rounded off to 17. A equals to summation of AS. Therefore, T can be written as 0.17 V by summation of AS. This summation of AS equals to AI A1 S1 plus A2 S2 plus so on AN SN. Number of absorbing material. This gives the reverberation time. Here V is the volume of the hall or the volume of the container, and S1, S2, S3 so on are the surface areas of the wall, ceiling, floor and different absorbing materials, and A1, A2, A3 so on gives the absorbing coefficients of different absorbing material. Reverberation time can be determined by the knowing the other quantities, right? So Sabine formula, according to Sabine, the reverberation time is directly proportional to the volume of the hull and inversely proportional to the total absorption. A is the total absorption, V is the volume of the hull, T is the reverberation time. You can write any of the answers as a reverberation as a Sabine formula. Next, coming to the vibrations. If a sound is produced from a tuning fork or any other body, when you are disturbing a body, it vibrates. The body vibrates with its own natural frequencies. There is no external influence of other forces. Just you tap your desk or bench, then the wooden sheet produces some sound. If you tap the iron metal of that bench, it produces different sound. If you tap a glass, then it produces different sound. If you clap your hands, then it produces different sound. And these all are their own natural frequencies. They are vibrating with the natural frequencies. There is no external force or external influence other than the impulse that initiated the motion. This type of vibrations are called as free vibrations. The vibrations of the body with its own natural frequencies under no external influence other than the impulse that initiated the motion is called as a free vibration. For example, if you vibrate a tuning fork, the vibrations of the tuning fork, oscillations of the simple pendulum, free vibrations of a spring, all this comes under the free vibrations. We are not giving any type of external force to this tuning fork and oscillating simple pendulum, vibrating string or loaded spring. All are vibrates with their own natural frequencies. It is called as free vibrations. If you're vibrating one body and you're putting this vibrating body on another body, then the second body also vibrates due to this vibrating body. For example, take a tuning fork and vibrate it, and take this tuning fork and put it on a desk, your table. Then the wooden table also makes vibrations due to the vibrating tuning fork. So actually there is no free vibrations in the wooden table or desk, but due to the vibrations of a vibrating tuning fork, it is vibrating. So here forced vibrations are there. Due to the forced vibration, the second body is vibrating That type of vibrations are called as the force vibrations. See here, this body is vibrating due to the force vibrations. So this type of vibrations are called as a forced vibrations. The forced vibrations examples can be given: the vibrations of a bridge under the influence of marching soldiers, and vibrations of the table and with the vibrating tuning fork. And you may experience when you are traveling by bus at some certain speed, the whole body of the bus vibrates with different sounds like that. It produces all the windows, all the window frames, and everything of the body, even your feet feels the vibrations at particular speed. The whole body of the body bus vibrates. And sometimes you may feel that the bike also vibrates in a particular speed. That is due to the vibrations produced in a engine, and the body is vibrating due to the engine vibrations, right? These are all the forced vibrations. If the vibrations, the body is vibrating with certain natural frequency, and it makes the other body to vibrate to its same frequency. For example, here tuning fork is make vibrated, and it is making vibrations, and you are putting this vibrating body to another body nearby the another body B. Consider this is a tuning fork A and this one is a B. Then due to the vibrating tuning fork A, the body of B, the tuning fork B also vibrates with the frequency equal to the A. This phenomena is called as a resonance. The phenomena in which the body vibrates with its natural frequency under the influence of another vibrating body of the same frequency is called as a resonance. It's a phenomena where the body, vibrating body, makes the another body to vibrate with its same frequency. See the amplitude of the frequencies: natural frequency, first body and second body. Blue line gives the first body and the second body, and the overall the resonance. So resonating frequency increases because this is a behaves like a constructive interference. And here we have a experiment by using resonance apparatus to find the velocity of sound. The examples for the resonance: if the military band or our school band, when you are celebrating parties and everything, some functions, and DJ or military band vibrates outside, then vessels in a home starts vibrating with the same frequency. You may have experience if in your party, in your farewell or welcome party, the DJs or sound systems produces some sound. If you are nearby the sound system, you may feel your body is vibrating, your foot is vibrating, the nearby utensils or the nearby objects also vibrating. That is due to the resonance. And in a case of tuning fork vibrates its own frequency, and the table also forced to vibrate at the same frequency. And if you have a pendulum system consisting of different lengths, 4 or 5 pendulums, one pendulum is moving with a certain frequency, natural frequency, then all of them moves with a natural frequency when compared to other frequencies. And if you put a different pendulums on the body, a table, then it produces natural frequency. A swing is a good example. It is like a pendulum with a single natural frequency depending on the length. If a series of regular phases are given to the swing, the motion can be built enormously. And the column of a soldiers. While soldiers crossing a suspension bridge, they are prohibited to march in steps and are advised to march on the suspension bridge out of steps so as to avoid the resonance between the natural frequency of the bridge and the frequency of the steps of the soldiers. This causes the collapse of bridge. So when they are crossing a bridge, suspension bridge, uh, they are advised to step down, step out the march fast. And tuning of radio, and sometimes we notice when our door is closed when quickly and very distance doors moves because both of them identical material and both of them in resonant. You are closing one door with a full power or full fastly, then another one also resonates. And in medical scanning, MRI, magnetic resonance imaging, good example for the resonance. And ESR, electron spin resonance, works used on based on the resonance. We have different applications in different areas, wide areas, wide scope has the applications of the resonance. And for if echoes, reverberation, resonance, force vibrations, damp vibration, all are producing here. If all these are present in a auditorium or hall, it is very difficult to listen a lecture or listen a show or whatever it may be. So according to the Saban, he given some conditions for good auditorium. So what a auditorium is said to be good if it follows these conditions. The quality of sound should be same in the entire hall. There is no high, low sounds in here and there. There should not be an echo. There should not be focusing of sound in a hall. Should not be any resonance effect. The noise should not enter into the hall or outside, inside hall. Sound should not go away from the hall. And reverberation should be optimum. The walls should be sunproof. Right? These are the if adequate loudness. Otherwise, all parts of the sound should be adequate. Otherwise, what happens? Sound may increase for the some of the persons who listens the increased sound, some of the persons decrease listen decreased sound. Optimum reverberation should be there, exclusive of extraneous noise. There is no footsteps, machinery, vehicles produce sound from outside should not enter. Uniform distribution of sound, right? Elimination of echoes, elimination of echoline effects. If there is the conditions, if it follows all these are the sound is distributed equally in all the areas of the hall, and no optimum reverberation is there, no echo effect is there, then that type of halls or auditoriums are called as a good auditorium, are said to be good for every purpose, right? In this class, we discussed about the Doppler effect, echoes, reverberations, resonance, and Sabin's formula, good auditorium conditions. From this area, you will get a good marks, and in competitive examinations also, you had a good scope to get the marks from this area. Right? Hope you understand the concepts and understand the applications. You focus on the definition and concept and applications of all these Doppler effect, echoes, reverberation, and reverberation reducing methods, resonance. Right? Thank you very much.